All right, so the other major existing quantum sensing technology is called a superconducting quantum interference device, or a SQUID. So this is a very sensitive magnetometer that's used to measure extremely weak magnetic fields, and it's based on superconducting loops containing something called a Josephson junction, which we'll talk more about because it's very important to understanding superconducting qubits in general. And so these SQUIDs are sensitive enough to measure magnetic fields as low as 5 × 10 to the minus 14th Tesla. And measuring fields that low typically require a couple days of average measurements. But to kind of put that into perspective, I kind of have the scale here of what some common magnetic field strengths are. So the Earth's magnetic field is around 10 to the minus 4 Teslas. So it's pretty big by comparison. The human heart has a magnetic field that's about 10 to the minus 10. And muscle impulses create a magnetic field that's like 10 to the minus 12. So those are all orders of magnitude larger than the sensitivity of a SQUID, which is crazy. And so one thing that you'll have to keep in mind as you think about how a SQUID works is we need a way to isolate all of that stuff from the SQUID for it to do its job. All right, so the DC SQUID was actually first invented in 1964 at Ford Labs, so the car company. And this was shortly after Brian Josephson postulated the Josephson effect, and folks at Bell Labs in 1963 first created a Josephson junction. So let's see, what is this Josephson stuff? So the Josephson effect is a manifestation of long-range quantum coherence of superconductors. So the simplified picture is shown here. So I have two regions of superconductor, and they're put pretty close to one another. And I have a quantum mechanical phase measured in each of these superconductors, and I can label them as phi 1 and phi 2. And in an ordinary material, the phases of these two different spots in my material are going to be unrelated. But in a single piece of superconductor, the phases of the two different spots would have some specific relationship related to the property of the material itself. So in this situation that I have in this drawing, if the two regions of superconductor are close enough together, even though I have this little barrier region between them, their phases are going to be related. And this isn't quite a manifestation of entanglement, but this is a manifestation, this is a quantum coherence. And so functionally speaking, electrical currents can flow between these two regions of superconductor with basically zero resistance. And that current that flows between the two is called a Josephson current. All right, so these Josephson junctions generally have a much lower critical current. That's the maximum current that can be carried before resistance begins to appear than the two superconducting pieces themselves. And that's kind of the unique thing about the junction. So these Josephson junctions are the active devices of all superconducting electronics, including superconducting qubits. And just like the transistor is kind of the essential active device in semiconductor electronics, this is kind of our fundamental unit in superconducting technologies. And people have built Josephson circuits with up to 1 million Josephson junctions. So the SQUID is a very simple Josephson circuit. It only involves 2 Josephson junctions. So in a SQUID, we have 2 Josephson junctions. Those are kind of in this shaded regions here. And they're connected in parallel in a closed superconducting loop. And the fundamental property of superconducting loops is that they enclose magnetic flux in only multiples of a universal constant called the magnetic flux quantum. And the magnetic flux quantum is very, very small. So therefore can be used to produce these extremely sensitive magnetic field sensors. So the magnetic flux quantum is 2 times 10 to the minus 15 Webers, which are volt seconds. So I'll just write volt seconds. And so I just sort of showed you kind of scale on the last slide. So this is, very, very small number. And the small fraction of the Earth's field that is not attenuated by the magnetic shielding in the SQUID magnetometer is something that needs to be carefully considered. So there's a lot of fancy electronics that are kind of built into the SQUID to make this all work. And so you can kind of model, how much magnetic field you're going to be inevitably experiencing from the environment based on properties of your shield, et cetera, et cetera. And so you can correct for those things. But those things have to be known very precisely. So in addition to sort of external noise, like the Earth's magnetic field, the SQUID sensitivity is also limited by the intrinsic noise in the device, which is in a 4.2 Kelvin niobium SQUID, which is kind of the typical instrument. It's typically about 1/millionth of a flux quantum. So the internal noise in a 4.2 Kelvin niobium SQUID is about 1 in 10 to the 6th, that's 1 million, of the flux quantum. So it's pretty small, which is nice. All right, so there's some inherent periodicity to the SQUID because it measures things in flux quanta and not in sort of an absolute scale. And you can do some electronic manipulation to get around that, but often we're just measuring things in a SQUID relative to some known standard. So it doesn't need all that fanciness. So if you look at some data taken on a SQUID magnetometer, it might look something like this. So I have temperature plotted on the x-axis here, and this is data taken at a magnetic field of 1,000 Oersted. And I'm measuring something called the magnetic susceptibility. And this is a measurement that's done a lot on paramagnetic molecules, for example. So if you have ever worked in an inorganic chemistry lab and made some transition metal complex that has unpaired electrons, this is definitely a type of measurement you'll want to make. Lots of people in our department do this kind of measurement. And it's also done on similar kinds of materials with unpaired electron density. So this is a vanadium complex. It has vanadium in a tren environment. This is this tetrachelating nitrogen ligand that's kind of a basket on the bottom here. And then it has a nitrile sitting on top of it. And it's vanadium in the 3+ oxidation state, and it has 2 d electrons, which you can kind of see represented in this energy level diagram. So in this energy level diagram, it has lots of interesting things. So I can excite this complex using some kind of light, visible light. It excites, that's the blue line, and it excites from the ground state triplet, which is shown here, to an excited state triplet, and then it undergoes intersystem crossing. So that's movement between excited states with different spin. So it moves to a singlet spin, and then it emits light from that excited singlet state. And so the energy, electron configuration of the excited state's there. And what's fun is that this piece right here, so you see the 0 state and the 1 state, this part of the molecule's fine structure can actually operate as a qubit. So this paper is all about designing a cool molecular qubit. And this fine structure splitting is nearly the identical picture that you get in something like an NV- center. So let's just walk through it for a second. So I have this D2 electron configuration. So 2 electrons in my system. And so as you see right here, this is an S equals 1. So I have 2 unpaired electrons. And there's 3 ways that I could draw 2 electrons in 2 orbitals. So I can draw them both spin up, or I can draw them both spin down, or I can draw them 1 spin up and 1 spin down. So little m sub s is equal to 1, little m sub s equals to -1, or little m sub s equals to 0. Those are my 3 possible spin states. And zero field splitting, in the absence of a magnetic field, allows you to differentiate between those states. So the little m sub s equals +1 and the little m sub s equals -1 are a little bit higher in energy than the little m sub s equals 0 state. Okay, so that's this guy. And so that state, that set of, or what's really 3 states, but it's kind of functionally operating as 2 states, can be a qubit. And D here is the zero field splitting. And if you are a molecular qubit person, you think a lot about how you can tune the properties of the molecule to change that energy, that zero field splitting. So how does this relate to this picture? All right, so I'm measuring the magnetic susceptibility of this molecule. So I'm trying to learn something about how the electron density is paired or unpaired as a function of temperature. And so at high temperatures, I'm measuring some magnetic susceptibility. It's 1, so I have unpaired electron density. And then as I go to lower temperatures, my magnetic susceptibility goes down. And so that's telling you about the spins pairing, because you're losing that sensitivity to the magnetic field.